Okay, Assalamualaikum warahmatullahi wabarakatuh, and a very good evening. So today we are assigned to do an assignment called Flip Classroom 2 or Assignment 2, basically on the topic refrigerant. So first of all, we need to describe the principle of vapor compression cycle from the course outcome. Second is we have to analyze principle of energy mechanism, and third is to evaluate solutions. So as the CO2 says, analyze principles of energy mechanism to solve vapor compression cycle. So we have been given a question to be settled. Okay, so in order to describe the principle of vapor compression cycle, first of all, you have to understand the TS diagram and the components involved in vapor compression cycle. So for vapor compression cycle, the basic components that has been involved is compressor, condenser, expansion valve, and evaporator. Okay, so by looking at the TS diagram, you can see where the energy coming into the refrigerant, coming out from the refrigerant, and where the power actually comes. As you can see, from in between 1 to 2, there is a compressor. So there is work done by compressor. At the condenser, there will be energy be released into the environment, and at the evaporator, there will be energy taken from the refrigerated space into the refrigerant to be processed. So for the question, we are using R134A as our refrigerant. Okay, so why do we choose R134A as our refrigerant? Firstly, because R134A has been developed to be chlorine free. Therefore, the chances of being bonding or mixturing with carbon will be lesser, so less CFC will be produced. And secondly is that in the textbook, it says the refrigerant should have a saturation pressure of 1 atm or higher at negative 20 degrees Celsius in this particular case. Therefore, ammonia and R134A are such two substances. Therefore, R134A is actually good to prevent any air leakage into the refrigeration system. Therefore, that's why we choose R134A.
Oh. Okay. As the refrigerant exit at saturated vapor at state 1, we can identify that we can identify the enthalpy, pressure, and entropy for that state. Okay. The enthalpy for state 1 is 269.03 kilojoule per kilogram. The pressure at 35 degrees Celsius, since the ambient temperature is 35 degrees Celsius, equals to 887.73 kilopascal. And the entropy, since it is saturated vapor, it is equals to entropy gas at 35 degrees Celsius, that is equals to 0.917155 kilojoule per kilogram Kelvin. Okay. At state 2, from the TS diagram, we obtain the state 2 equals to superheated vapor. Therefore, the pressure it is a bit higher than the P1. So from the property table, we obtain that P2 nearly to 35 degrees Celsius, P2 higher than 35 degrees Celsius is equals to 0.9 megapascal. Okay, so we can obtain the temperature saturated, the H2S and S2 from the property table. S2 is equals to, however, S2 is equals to S1 equals to 0.917155 kilojoule per kilogram Kelvin. The H2A can be obtained from the efficiency from compressor. Ada yang tertinggal ke? Ada yang? Terus record ke ni? Oh sorry. Okay. For state 3, from the TS diagram, we obtain that it is at the saturated liquid line. Therefore, the pressure for state 3 equals to pressure at state 2, 0.9 megapascal. And from property table, we can obtain the H enthalpy and entropy for the state. At state 4, the pressure for state 4 equals to pressure at state 1. And the enthalpy for H4 is equals to enthalpy at H3, since it's throttling. It's equals to 101.61 kilojoule per kilogram.
Okay, for the another task, so I gonna solve the required refrigerant mass flow rate if the desired cooling effect is 10 kilowatt. So based on the general equation, the QL equal to m dot product with H1 minus H4. So we can get the mass flow rate, which is 0.05797 kilogram per second. So okay, so that the mass flow rate. So next is so this is the, as the efficiency has been stated, so we use the efficiency to get the value of the H2A. So based on the general equation, so we can get the value of H2A, which is the enthalpy actual, is 269.3175 kilojoule per kilogram. Okay, next, so we gonna have the how much the coefficient of performance for the selected operation pressure. So as the general equation, so to get the COP, so we already have the QL, but we have to calculate the value of Win. So based on the formula for the Win, the m dot is 0.0597, product with 269.26 minus 269.03, which is H2S minus H1. So we can get the Win value, which is 3.5957 kilowatt. So as we substitute in the formula, we can get the COP of, which is the coefficient of performance for the refrigerant, which is 2.78. Right.
So finally, for the final question, which is to choose the improved system, then we have choose Cascade refrigerant cycle. So basically, this is our pH diagram for Cascade refrigerant cycle, and this one, as you can see, the QL, QH, Win and Win for lower and upper. And this one for TS diagram for Cascade refrigeration cycle also. And as you can see, this one for lower side, for lower part B, this for QL, Win, and for state 6 to state 5, Win, and for the upper and QH. So that's for Cascade system diagram. To compare with our ideal system, and basically after the analysis, we identified that the W in net for the Cascade refrigerant cycle is this value, and for the COP for Cascade is 82.92. And to compare with our ideal system, this is for W in net for ideal system, and COP for ideal is 2.78, which is for the comparison between both systems, we identify that Cascade can produce a higher COP than Ideal, which is good for the system. And finally, for the comparison cost between Cascade and Ideal, we identify that basically we refer this value from the TMB, which is basically 21.8 for the month, but then we convert for the hour, and this value is we get 43 ringgit and 42 cent for Cascade for 12 hour, and for Ideal is to 1,294.45 cents for Ideal. So that's all from our group. Thank you.